Hi everybody, welcome to another video in Calculus 2. This section 8.8, we will do numerical integration. Pretty much it's just an approximation of the integral. We focus on three things, the Midpoint Rule, the Trapezoid Rule, and the Simpsons Rule. Like I said, we focus on the approximation, not on the error, but we still need to know the basic of the error approximation. Right, so let's look at the first example. Absolute error. So pretty much what we have here is we have the exact solution x. Usually we don't know that unless it's easy to calculate. And c is an approximation of x. And when we take the absolute values of the difference, we say that is an absolute error. And if we take that absolute error divided by the absolute values of x, that is the relative error. So let's look at the first example here. By the way, in this section we use a lot of calculator, so make sure you have that ready. And I'm going to use the TI-84 because I think it's easy to do what we do here. Right, so the ancient Greek used 22/7 to approximate the values for pi, determine the absolute values, absolute and relative error. So first, pi, of course, is irrational number. Right. So that as far as I can remember. In the calculator, if we hit second pi, that's what we have. So now we just find the absolute error and the relative error. So that's pretty straightforward. So absolute error. It doesn't matter which one minus which. Just going to take the approximation. And if we use a calculator, just put pi. So we have, we don't even hit the absolute value, just take 22/7 and subtract pi. If it's negative, just turn to positive, and just write 0.00126. Which is kind of good approximation. Next, the relative. So relatively to the actual values of pi. We're going to take the approximation, subtract the actual values, divide by the actual, or the exact solution. Yeah. So like I said, we put absolute value, just make sure that everything will turn out to be non-negative. So if we know the values in the calculators there, it's good, so we're just going to say it's just 0.00126 divided by pi. We don't even need absolute values of pi because that's positive, but that's how we write it in a calculator. We're just going to say it. We're going to take that. Oh wait, that would be wrong. Open parentheses, 22/7 minus pi divided by pi. If it's negative, we turn it back to positive, right? So 4 point, so like that. 4.025, let's say. The e there means times 10 to the negative 4. So if we want to rewrite this, it's going to be move to decimal place. We have 4025 decimal. Originally was right to 4. We move 4 unit, 4 place to the left. 1, 2, 3, and 4. Right. So 1, 2, 3, and 4. So will be that, and just ignore the dot. Or in the calculator, if we just said, let's just write, right, if we keep that in the engineering, when we do this, it only gives us in the 3 or the 6 a multiple of 3. So it just gives to, like I said, multiple of 3. But keep normal. Depends how many decimal places do we want to keep. I mean, significant figures we want to keep. Right, so that's first one. Next, another approximation using this one. I think the Chinese use this. So, of course, that's a little more complicated. So we should expect that a little more accurate. And only ask for the relative error. So we have 355 divided by 113, subtract pi, divided by pi. Oops, make sure you have the parentheses, divided by pi. Right, we have that. Now, of course, compared to this is a much better approximation because the error is extremely small compared to that. But right now we're not using any of this anymore because the calculator knows pi. We'll just use pi. Right, so now, like I said, the focus here is how do we do this? The 3 methods: Midpoint Rule, Trapezoid, and Simpsons Rule. As long as we know how to do those, that will be fine. So the first one is the Midpoint Rule. So it's like we did in the Calculus 1 where we learned about Riemann sum. This is pretty much like that, and we use the midpoint. Right. Suppose f is defined and integrable. So that's the condition for the function. The midpoint rule approximation is so we have n equally spaced. So this will be given, and an interval will be given. And the midpoint rule is that. So regardless of the rule we're using, it's always the width of a rectangle. In this case, the rectangle is b minus a divided by n, and we let that equal to delta x. It's always, doesn't matter what method we're using, it's always this. And that is the first thing we find, because like I said, n will be given and the interval a and b will be given, so we can find that. So pretty much we just find the midpoints and then we evaluate the function at the midpoint. So the values, so mk is the midpoint, and the function at the midpoint, this is going to be the height, and because delta x is the width. In this particular case, height times width give us the area of a rectangle. Add on them up, we have approximation of the area. So for example, kind of difficult to see here, but we go from A to B, and in this case we divide that into interval like this, equally spaced up, not that point, sorry, I wrote that terrible, sorry, yeah, should be equally spaced. And in each interval we're going to take the midpoint of that, find the height, and we have one rectangle. Height times width give us the area of those rectangles, and so pretty much we use the midpoint to find the area. So first rectangle, second, and then so on. Just use the midpoint to find the height. And then we add all of up, we have the area of the whole thing. Right, so let's see how it works in the first example. We're going to do by hand first, and then we use a calculator. So approximate the integral from 2 to 4 of x squared using the midpoint rule for subinterval. So, and usually the picture is nice, but just draw an interval. All right. So we have an interval going from 2 to 4 and divide to 4 subinterval. So we just say divide this into 4 equal segments. Let's say 2 is there, 1, 2, 3, and 4. So we're going to 2 to 4, and we divide that into 4 segments. So like I said, the first thing we do is find the width, delta x is equal to b minus a divided by n. In our particular problem, going from 2 to 4, so 4 minus 2 divided by 4 is 0.5. So 0.5 is the width of one interval. So we go from 2, add a width 2.5, and then 3, 3.5. So those are the points. Next, this is the midpoint rule. So we're going to use the midpoint. So midpoint midpoint of 2 and 2.5, that's easy, 2.25. 2.75, 3.25, and 3.75. So those are the points, the midpoints of the intervals. Right, so here we have from 2 to 4, divide to 4 equal pieces, and then find the midpoint. After that, after we have the midpoint, I just want to put that in here for the midpoint. We find the height based on the midpoint, and then we multiply by the width. So the approximation, let's say this is an integral I approximately equal to, we just said the function at those values. That gives us the height, and then we multiply by the width, give us the area. The width give us the area of the first rectangle, and then so on. and then factor out delta x. We will have just the sum of all of this. So that's simple enough. So what we do here is using the calculator. So a TI 84, right? So and for some reason the calculator frozen. I have to reset it. Right. Now, so first we're going to find the point, the midpoint. I will use that using the curly bracket. You see above the parentheses, there's the curly bracket. So hit second, open parentheses. I'm going to enter the numbers 2.25, comma 2.75, comma 3.25, comma 3.75, and that's all of the point. And I put second close parentheses to close the bracket. So enter all of numbers in the list, and then we hit the store key here, the STO, and then we store that into the list 1. You see above number 1 there's a L1. So in that case, list 1 will contain all those 4 points. Then another way to do this is hit stat and then edit. We can enter those numbers manually. If you want to clear this, highlight the list, highlight it, never hit delete, highlight it and hit clear. And then here we can enter that. It will be the same. Either way, we should have those numbers into list 1. Right, when we're done second mode. By the way, we can use the parentheses, second parentheses and the comma, or we hit stat and edit and enter the number that way. Either way, have those numbers onto list 1. Next, we need the function x squared, right? So let me just write this on the calculator. This is how we do. So we have 2.25, 2.75, 3.25, 3.75, store into list 1. And we know the store key is this. And enter the curly bracket and the comma. So will be those 3 keys. Right, so we do that first. Next, we store the function. So y1 equal to x squared. So hit y equal 2 and we enter x squared. When we're done second mode, quick. Now we will evaluate the function at this point. So we do either we hit variable, y variable, function y1. That's one way to do that. Once again, variable, y variables, function y1. One way to do that. Another way is alpha, trace, and there's y1. If your calculator does not have the bottom menu, that's fine. Just go variables, and then here I have that option. And we evaluate at all of the point here. So it will be second number 1. And have those values. And then finally, we're going to add all of this up. To add all of this up, we hit, it is in the stat, so hit stat, second stat, and go to math, option number 5, and then second, the negative sign. So we're going to add everything on that list. Right, so we have that. So one way to do it this way. Another way to do this is, again, second stat. Go to math, option number 5. If your calculator you can move up, then we just say we're going to add all of them up. That is 37.25. And then, so that gives us everything in the parentheses here. And at the end, we multiply by delta x. So we can do that, or we're just going to do the summation of that, and then multiply by delta x, which is 0.5. So we're just going to do all of this. So once again, second stat, go to math, option number 5, and then alpha trace y1, second 1 L1 multiplied by 0.5. So that is 18.625. Right. So let's recap the L1. If we want L1, that is second, and then number 1. Of course, the curly bracket, we talk about that. It is second, and the parentheses. The summation. Second stat. And go to math, option number 5, give us the sum. Right, so that's what we can do. Right, if we want the exact values, we can always do math number 9, integral from 2 to 4. I just want to see how good the approximation is. Remember, this section, they do not want the actual solution. They want the approximation. So this is what we have. Right. So simple enough. Next, approximate that integral using midpoint rule with 5 intervals. So we go from 0 to pi over 2. Right. So first I'm just going to draw the interval and 5 points. So 1, 2, 3, 1, 2, 3, 4, and 5 interval, and we go from 0 to pi over 2. First we find the width, as always. In this particular case, we have pi over 2. Minus A0 divided by 5. So that gives us pi over 10. So each one of them is pi over 10. Two pi over 10 is pi over 5. 3 pi over 10. And and then 4 pi over 10 is reduced to 2 pi over 5, and then 5 pi over 10 reduced to pi over 2. So those are the point on the interval, the endpoints of the interval. What we do is we use the midpoint. The midpoint of the interval. Simple enough, right? Between 0 and pi over 10, that pi over 20. Between these two, we're just going to add pi over 2. The width is pi over 10, so I'm going to add a pi over 10 from it. Give us another midpoint. So we just go with pi over 10 plus pi over 10. So what is 1 over 20 plus 110? So that is fractional. 3 over 20. Right. Here what we can do though. First, you're going to hit pi over 20, so 1 over 20. Let's do fraction. 1 over 20. Hit enter. That's good, right? Next, we're going to add that. Take that. So, second negative sign, which is the last answer stored in the calculator. By this, it's going to be that number, 1 over 12. We're going to add a fraction of the width, pi over 10. So 3 over 20, right? And then the nice thing about using the answer is we just hit enter. Give us the next one, 1/4. I forgot the pi. And we just hit enter. Just take the last answer and then add the next one to it. 7 pi over 20. One more time. 9 pi over 20. Right. So once again, I start with initialization of pi over 20. 1 alpha y equal to 1 over 20. Hit enter. So I have to store the answer. So the answer, when every time I hit second answer, it will be the last number stored in the calculator, which is that. And then we just add the increment of fraction of 1 over 10. If we use the fraction notation, it's going to give us in fraction. Or if you don't want to, we can just say, let's check the answer, plus 1 over 10, which is the width, and then we have to store the answer in fraction. So hit math, fraction. So we have to enter it like that, and it works just fine. Those are the points. Right. Next, we evaluated all those points multiplied by the width. So the integral approximately equal to the values of all of those. Now we just factor out and then multiply by the width at the end. So we have the values of pi over 20 plus 3 pi over 20 pi over 4, all the midpoints, and 7 pi over 20, actually there's one more, 9 pi over 20. All that multiplied by the width. Right. We use the calculator though. So we store those values. Onto a list, and then we say the function is cosine of x plus 1. Make sure this is in the radian mode, and after that we say sum. We're going to add on the values of this one, evaluate as y1 multiplied by the width. Right. Now the list second curly bracket. If we use this to store, the list will just update by itself. Second pi over 20 is 3 pi over 20, 5 pi over 20, which is pi over 4. Seven pi over 20, and 9 pi over 20. Curly bracket. We have those fractions. Right. Make sure it is in the radian mode before we enter the function cosine of x plus 1. Right. We enter the function, so second mode. Right, we just need to enter this. Second stat, go to math, option number 5, that summation, and then I can do this variable, y variable function y1, evaluate at the list that we just entered. Did we store that into a list? Right. And then multiply by the width, pi over 10. Right. Did we store the list one? Yes. Nope. We did not store this into list one. Right. Have to do this again. So we enter all of that. Make sure we have to store that into list one before we can do anything. So if you want list one, make sure it's that. Right. So second stat, make sure you store make sure make sure that the number store into the list. And then second stat, go to math, option number 5, alpha trace y1, second one, this one, times, open parentheses, pi divided by 10. That is 2.57. Just make sure that this is kind of good. We have to just do the approximation using the calculator. As you see, the approximation is relatively good. Just make sure that makes sense. Right. So that is the midpoint rule. We have all the interval and then take the midpoints. Next we have the trapezoid rule. The trapezoid. So first of all, let's look at the trapezoid. I'm not going to draw that sideways. It's upright like this. A trapezoid. Or in the trapezoid, let's say if we have the turn this sideways, we have the height, the two bases. So the height, and then this is called the base number 1 and base number 2. The area of that is base 1 plus base 2 divided by 2 times the height. So that is the area of one trapezoid. And what we do instead is going to be this. Now, this is my attempt to try to prove this. So let's say I'm going to try to draw an interval. Right. So we go from A to B. And we're going to draw the trapezoid. So, just get the idea. Think about this, the trapezoid. Let's say that is the first trapezoid. And then we draw the second one. And then the third one. So, now think about this. Let this be A or X naught. X1 is the first endpoint, X2 is the second endpoint, X3, and so on. So what we see here is, if we want the area, I'm going to write in, instead of writing like that, because all of the trapezoid have the height, I will factor the height toward the end. In this case, the height is also delta x. Right. So instead of writing this form, I'm going to write in this form of area is equal to B1 plus B2 times the height divided by 2. Right, those formulas are the same. However, we're going to put this form and factor out the height divided by 2. The height in this case is delta x. So pretty much delta x divided by 2 is factored out. So in that case, the area of the first one is going to be the values at x0 plus the values at x1. All of that times delta x divided by 2. So that is the area of the first trapezoid. The second one is going to be the function at x1, so base 1, base 2, and then delta x divided by 2. So that's the area of the second one. And then we factor out the delta x over 2. And if we keep doing that, what we see here is, so the integral is approximately equal to, what we see is f of x0, f of x1, and then f of x1, and then we have f of x1, f of x2, and the next one will be f of x2, and f of x3. Bottom line is, when we do all of that, we factor out delta x over 2. Of course, when we do this, if we count, you can see that combine like terms. So in the sense, when we look at this, we see we have one on the left and one on the right. But every endpoint in the middle, there should be two of them, one and one in the other two, the other. Right, so I have one on the left, one on the right. Everything every endpoint in the middle, there are 2 of them. We'll do all of that, delta x divided by 2. So that's what the trapezoid rule is. Right. Let's look at an example. Again, same problem. Integral from 2 to 4 x squared. Now use the trapezoid rule. For interval. So as always, the first one is calculate the width. So we have 4 minus 2 divided by 4. That 2, 0.5. So I'll just draw the integral first. Right. 1, 2, 3, and 4. Going from 2 to 4. Right. The interval is 0.5, so the increment is by 0.5, 2.5, 3, and 3.5. So those are the points that we use. The coefficient though, in the trapezoid rule, just use different colors here. In the trapezoid rule, the coefficient is 1 on the left, 1 on the right. Everything in the middle, there are 2 of them. Those are the coefficients. So if we want to do this by hand, the approximation of the integral is approximately equal to, we only have 1 on the left point, 2 in every midpoint, every endpoint in the middle. That's what I should say. And then 2 and then 1 point on the end. Close that, and then with times in the formula say delta x divided by 2. Remember, height divided by 2, so delta x divided by 2. Right, so that is the trapezoid rule. Right, now we're going to do this by hand. By calculator. So first, same thing. I'll store these values into L1. So 2, 2.5, 3, 3.5, and 4. Store into L1. Now actually I will store the L2 into it too, into the list. So the coefficient will be 1. There are 3, 2, 1, 2, 3, and then 1. Store this into L2. Now we need two lists, 1 for the values, 1 for the endpoints, and 1 for the coefficients. Right. After that, the y1, the function, is equal to x squared. And finally, the trapezoid rule is going to be the summation again. So first, we're going to have the y1 at L1. So we evaluate the function at the list. So that goes, and then multiply by L2. Actually, when we evaluate we multiply by L2. And when we write like that, the calculator understand that evaluated all of the first point multiplied by the first one of L1. So it multiplies point wise. There are 5 values of this and then 5 values of this. They just multiply together. And at the end, we have delta x divided by 2. Delta x divided by 2 is 0.25. So we're just going to do this. Right. So open curly bracket 2, 2.5, 3, 3.5, and 4. Close curly bracket. Store into list 1. So we have those values. Next, the coefficient 1, 2, 2, 2, 2, and 1. Close curly bracket. Store into second number 2. So we store the list. By the way, if we want to make sure that it is corresponding, hit the stat and edit. You have those list 1, list 2. Look good. Second, quick. Right. The values of the function. The function is x squared, right? So that's good. Now we will do summation. We're going to add all of them up. Alpha trace y1 evaluate at list 1 times list 2, and all of that multiplied by delta x divided by 2, which is 0.25. And we have 18.75. Earlier we used the midpoint rule and we get that, and this one kind of close to it, so that's fine. That looks fine. Right. Next, I will try to evaluate that. Now actually we know, assume that if it is given in that. Now find the absolute error using the midpoint rule and the trapezoid rule. So actually we have to do both midpoint rule and the trapezoid rule, and after that subtract this actual values to find the absolute error. So first, midpoint rule. So as always, I'm going to draw the interval and then have the numbers. It is much easier to get the sense of what we have. Right. So from 0 to 8. Before we do anything, whatever, doesn't matter what rule we use, always find the width first. So now what is the increment? The increment is 1 over 8, right? Right. So I'm just going to draw the interval. Right. We start with 0, and that will be 8. 1, 2, 3, 4, 5, 6, 7, and 8. So we have 0 and then 1. Each increment is 1/8, so we have 1/8 plus 1/8, 2/8 plus 1/8 plus 1/8. Just going to write like that: 5/8, 6/8, and 7/8. And then the midpoint. So the midpoint actually going to be half of that. So this is the midpoint. It's going to be 1/16. Right? Half of 0 to 1/8. So we're going to have 1/16. Just use fraction though. 1/16. Hit enter. So that store that into answer. And then we should say answer plus the width is 1/8. So from the midpoint, go another width of 1/8. Right, the next one is 3/16. And then 5/16. Now we see the pattern. Next one is 7/16. It is. Now just keep going. And then 9, 11, 13, and 15. Because we just keep hitting enter. In this we have those points. And the midpoint rule is we evaluate at on the midpoint multiplied by the width. So first, and later on we just said all of this into L1, and then we just said we will evaluate at Y1 and then multiply by the sum. So that evaluate all the function, and then at the end multiply by delta x, which is 1/8. Right, now second, open the curly bracket. Now I just enter on the point. 1/16. There's another way to do this though, but I'm not see if it's worth. Yeah, I'm going to do that too. Close curly bracket and then store into this one. Right, that's one way to do that. Another one to do that is using the sequence. Instead of hit I think we just hit second stat. So second stat, instead of go to option number 5 for the sum, we go to the tab, second tab, on to number 5. Right, the expression is what? So we're going to need the midpoint. The midpoint is starting from 1/8. We're going to add the width. The width is x. The width, the first one there's 0, and then there are 8 of them. And we increase by 1 every time. Right. So what does that mean? So originally we have 1/16, sorry. and then we're going to add the width to it. So the first one has no width. The second one we have one width. The next one will just say you add one of the width, 2, 3, 4, 5, 6, and then 7. So that's why we have from 0 to 7, and the increment is 1. So just paste, and we have those the same thing. Like I said, I'm not sure if it's worth, just type everything. Right, so we have list 1 there, right? And then we just need to do this for the midpoint rule. Summation, second stat, go to math, option number 5, summation 1. If your calculator does not do that, don't worry, hit variables, y variables, function y1, and we evaluate at least 1 on the midpoints, and then multiply by the width of 1/8. So we have that. Right. Now the absolute error. We're going to take these values and we subtract the actual values. And so approximation, the exact values. So we're going to take that, subtract 1 minus e to the negative. I mean, there are 2 of them, right? So we have that. Right. That is the midpoint rule. Right. Next, we will have the trapezoid rule. First interval is going to be the same. So we're going to have this point. Two, 3, 4, 5, 6, 7, 8. And going from 0, 1/8, 2/8, 3/8, 4/8, 5, 6, 7, 8/8 is 1. Right. So in trapezoid rule, we're going to use this endpoint. So when we do that, let's store those into this one. Now the coefficient. We have 1 on the left, 1 on the right. Everything in the middle, count twice. And we're going to store that into L2. And then the formula for trapezoid rule, we will take the summation of all the values of the function at y1 and then multiply the list 2 and then we have the width. Notice that in Trapezoid Rule, we have delta x divided by 2. Later on, the Simpsons Rule, this is divided by 3. So, midpoint, delta x, trapezoid, delta x divided by 2. In Simpsons Rule, delta x divided by 3. So, like I said, in this section, there's a lot of little things. I just want you to focus on the actual rules. How do we evaluate the function? Right, so just do that. So first, let's store the numbers 0, 1, 8, 2, 8, 3 divided by 8, 4 divided by 8, 5, 6, 7, and 8 over 8 is 1. Right, I will store this into second. Store this into L1. I shall have those values. Next, the list 2. The coefficient 1, and then how many 2? There will be 6 in the middle, 1 on both ends. Let's see, 1, 2, 3, 4, 5, 6. Actually 7. Sorry. 1, 2, 3, 4, 5, 6, 7, and 1. Store into list 2. Right. If we just make sure that there's a corresponding, hit that and edit. So there is the corresponding. Actually, I think it's better for L2 enter in here. I'm going to do that in the next prompt. Right, so we have list 1 and list 2. Now we just need to do this. So we're going to add the summation. So we have the values of the function. I can just do this. Y1 evaluate at list 1. So the values of the function multiplied by the coefficient list 2, all of which multiplied by delta x divided by 2. Delta x is 1, 8 divided by 2 is 1 over 16. So we have that. And then the absolute error. Is that subtract the exact values. Exact values. And so we do that. Sorry. So we take that number, subtract the exact values of 1 minus 2 e to negative 1. So we have that. So if you get, forgot the 0. Got the idea that the midpoint rule actually more accurate than the trapezoid rule. Later on there is some reason behind that as well. So midpoint rule just have the dx, trapezoid rule direct divided by 2. Now we go to the Simpsons rule, that will be divided by 3. Right. So the Simpsons rule. Suppose that the function is defined on the interval and we have n equally spaced. So pretty much the same thing. N equally spaced from A to B. So first always the width B minus A over N. Always that. and then we evaluate the function. So what we see here is the coefficient is 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, and then 4, 1. By the way, in the Simpsons rule, n is an even integers, so it has to be even. And the width is still the same thing. And it can be shown that the Simpsons rule for 2n is equal 4 times the trapezoid rule and minus the trapezoid rule at n divided by 3. So we can use that. But now, let's just see how the Simpsons rule work. So first, in this example, we go from 0 to 1 and 6 sub-interval. So we'll go from 0 to 1. It'll be 6 sub-interval. One, 2, 3, 4, 5, and 6. First thing we do, of course, always the width. So 1 minus 0 divided by 6 is 1 over 6. So the width is 1/6. So the increment from the first one is 1/6. So we have 0, 1 over 6, 2 over 6, 3 over 6, 4 over 6, 5 over 6, 6 over 6, which is 1. Right, so that's good. Of course, we're going to store all of this into L1. Now the coefficient in the Simpsons rule is different than the trapezoid. Trapezoid rule is 1 on the left, 1 on the right, everything in the middle. There are two of them. Now, for Simpsons rule, we have 1 on the left and 1 on the right. So those still the same. But the coefficient is going to be 4, 2, 4, 2, 4. The next one is 2, but actually just have 1. So I just want to go briefly why do we have that. So think about this. The Simpsons rule, we use pretty much the parabola to approximate. So instead of using a trapezoid like that, 2 trapezoid, we're going to use the parabola to approximate. And the reason to that is the trapezoid rule, the linear function, which is a straight line, and the Simpsons rule, we use the curve, and the curve is always closer to another curve because it doesn't matter what the function might go like this. When we cut into pieces, we can use a parabola to approximate the values of the function. The parabola is a curve itself, so we should say that it makes sense that the curve is actually will be close to the actual curve. The straight line is not a good approximation compared to the curve. So we use the parabola. So the parabola is kind of 1, 2, 1, kind of the sense of coefficient. So we're going to have 1, 2, and 1 for the first set of points, and then we're going to have 1, 2, and 1. So we just have to do that. Actually, it's not 1, 2, 1. It's 1, 4, 1. Sorry, because that is the square. So 1, 4, 1, and then for the next set of points, so we have 2 more trapezoid, and then the approximation is another parabola. So another 1 4 1, and there will be another 1 4 1, and we'll just keep it like that. Now if we do that, when we add all of them up, the coefficient will be 1 4 2 4 2 4, and then keep going like that. So that's why the coefficient is that. Because of the parabola, so the coefficient 1 4 1. Actually, we need a little more than that to show the coefficients 1 4 1. But if we want one piece, it should be 1 4 1. If we want to have two, there will be the overlapping one, so that make it a 2. Bottom line is it's going to be 1 and 1 on the end, and the middle 4 2 4 2 4 2, and it's all work with an even number. So anyway, I store that into L2, and then still the same thing though. Right, I need to go back to the previous example because I forgot to write up the y1 on the previous example. Have to be x e to the negative x. Sorry about that. So don't make this mistake. Make sure you have to enter the function. Right, so we're going to do this again, but this time the y1 is the correct y1. So I apologize for that, but at least now you know that is very important, that the y1 have to be, we have to store the correct function into it. Right, so some values of the function, and so it's still the same. So make sure you enter the function, even though that is the easiest thing to do, but don't forget that. So we have that. Subtract 1 minus 2 times so we have 0.0013. Much better. Sorry about that. Have to have the function. Right. So hopefully this still store all the same values though. Oh, good. Yeah, I still have all the midpoint. And then the midpoint rule. Summation. The values of the function. At least one. Times delta x of 180. So it's like I said, very important that we have to store the function. Otherwise, of course, it's completely off. So we have that. Subtract the actual values. That's more like it. Sorry about that. Right. So, like I said, the midpoint rule should be more accurate than the trapezoid rule in general. We should have that. Right. Sorry. Don't forget, we need to enter the function. Right. So, we have list 1, list 2. Make sure we enter the function is sine of pi x. And then the Simpsons rule is the summation, the values of the function at list 1 multiplied by list 2, and in the Simpsons rule we divide by 3. Right. So we store the number in the list 0, 1 over 6, 2 over 6, 3 over 6, 4, 5, and then 1. Close the curly bracket, store into list 1. So we have that. Right? Now, it's better to enter the coefficient here instead. Or to calculate, stat, and then edit. Now I just need to clear this list. Highlight the L2, hit clear, and hit enter. The reason I want to put it here because I can track the coefficient nicely. So there's the corresponding between the coefficient and the endpoints. Right. So summation second stat, option number 5, the variable at all those points. So list 1 times the coefficient multiplied by delta x, which is 1 over 6, divided by 3. So the Simpsons rule is divided by 3. Delta x divided by 3. And we have that values. And once again, I make the mistake. Make sure we enter the function sine equal to pi x. And make sure that it is in the right mode. Right. So we have that. Let's do this again with the correct function. Right. Right. Let's actually find the actual values and see what happened. Math, option number 9. Let's go from 0 to 1. And the nice thing about this is we enter the function here already. Just hit 1. That will be good enough. As you see, this is very good approximation. Right, so that is the Simpsons rule method. So once again, in the Simpsons rule, the summation of the values of the function times the values of the function times the coefficient, and then the width delta x divided by 3. For the width, for the trapezoid rule, this is divided by 2. For the midpoint rule, all the coefficient is 1, so we just have that, and multiply by delta x. So midpoint rule, delta x, trapezoid, delta x divided by 2. Simpsons rule, delta x divided by 3. Now, the error estimate. Now, for the midpoint rule and the trapezoid rule, we need the function that has the second derivative that is continuous. If the second derivative continuous, then the error, the maximum error, is equal to this. And for the trapezoid, is equal to this. Again, delta x we know, and what is k? K is the maximum or the highest values of all of the second derivative. So as you see here, in the midpoint rule is divided by 24, in the trapezoid rule divided by 12. Of course, when we divide by the bigger number, we have the smaller number. So that's why in general, the trapezoid rule should have the smaller error compared to the midpoint rule. I'm sorry, I take that backward. The midpoint rule divided by 24 is going to be smaller than the trapezoid rule divided by 12. Of course, divided by the bigger number is going to be smaller. So this one is smaller than that. Smaller than by the factor of 2 in exact. Right. In the Simpsons rule, we're going to need the fourth derivative, and we take the fourth derivative going to be less than k, so k is an upper bound of all of the fourth derivative, and the error in the Simpsons rule is divided by 180. So this the Simpsons rule, because we use the curve is actually closer to another curve than the straight line. So this approximation in general is better than those two. I stopped the video earlier, but I think we should have one more example. Alright, let's see. We try to approximate this integral. So consider integral from 0 to 3 of e to the x dx. Right. See the first one. Let's approximate using Simpsons rule. And after that, we will estimate the error. Let's use 5 subinterval. And 2, estimate the upper bound for error. So what we do is we're going to calculate this, and this is called the error for Simpsons rule. This is the upper bound for the errors. And actually not the upper bound, an upper for errors, and then actually find the actual error, find the absolute error. That is one of them. Right. So absolute error is ES. Right. So first, let's do the Simpsons rule. By the way, one of the important in the Simpsons rule is that the number of intervals have to be even. So let's do 6 instead. Right, that better. Right, so I'm going to draw 6. Going from 0 to 3, there will be 6 sub-interval. 1, 2, 3, 4, 5, and 6. The first thing, always do find the width first. Delta x equal to b minus a divided by n. So what we have is 3 minus 0 divided by 6. We have 0.5. So 0.5 is the width of one interval. So going from 0 to 3, the each increment is 0.5. Right. So 0.5 at 0.5 is 1, 1.5, 2, and 2.5. So those values we're going to store into L1. Next, we find the coefficient that corresponding to these endpoints. The coefficient in Simpsons Rule is 1 at the end and 4, 2, 4, 2, 4, 2 at the middle. So the coefficient 1 at the end, and then 4, 2, 4, 2, 4, 2, 4, 2, and then 4. Right, so that's why it has to be even, otherwise it doesn't work. Right, so to avoid any error that I did earlier, to make sure the first thing we do is let's just store the function. It's e to the x. Right, so y equal to second ln e to the x power. Right, just put that in first. And next we have list 1 and list 2. 0, 0.5, 1, 1.5, 2, 2.5, and 3. Store to list 1. And then the coefficient 1, 4, 2, 4, 2, 4, 1. Store to list 2. And then the Simpsons rule is going to be sum the values of the function times the coefficient. And in Simpsons rule we have delta x divided by 3. Right, so that is the Simpsons rule. So I will store these values. 0.5, 1, 1.5, 2, 2.5, and 3. Store that into list 1. Right. So one way to enter the list, and then we can do the same thing for list 2. Or you can just hit that, and under edit, you can enter the coefficient here as well. 1, 4, 2, 4, 2, 4, 1. So this way we know there's a correspondence between L1 and L2. So that's good. Like I said, we can do that, or we can just hit that and edit. If we want to clear a list, highlight the list and hit clear, it will clear the list, but I don't want to do that. Alright, so we have list 1 and list 2 into the calculator. We have the function into the calculator. Make sure you have that. Now we're going to do the Simpsons rule. So we have the second stat math summation. Option number 5, variable. So either alpha, trace, or his variable, y variable, y1. Evaluate that at list 1 times list 2, second 1 for L1, second 2 for L2, and close that, multiply by delta x 0.5 divided by 3. Simpsons rule divided by 3. So we have that. 19.09197. So that is the Simpsons rule. Only works for an even interval. Right, 2. Find an upper bound for error. So an upper bound for error. So the maximum possible error is given by, what was that? Yes, sorry. I mean that. So the actual error is less than that. So an upper bound for error so it is going to be equal to k b minus a divided by 180 delta x to the 4th power, where k is the maximum of all the 4th derivative. And of course, for x between 0 and 3. Right. First, I choose this example because we have e to the x, so derivative is very easy to evaluate. Derivative of e to the x is also e to the x, and when we take the 4th derivative, it still is e to the x. So we have the 4th derivative. Now, from 0 to 3, what is the maximum for that? Right. So for x between 0 and 3, the maximum of the 4th derivative is, now if we look at the exponential function, it goes like this. So from 0 to 3, the maximum will be at the endpoint of 3. So we say the maximum of that function is EQ. The right endpoint is the biggest one out of all of this. So in that case, we're going to let k be that biggest values. So I'm going to choose k equal to EQ. By the way, this is an upper bound. So if we want to, we can choose something bigger like e to the 4th, e to 3.5, pretty much anything bigger than this is fine. But k cannot be smaller than this. Yeah. So this an upper bound, whatever that number is, we can always make it bigger. So if we're not sure about it, we just make a little bit bigger. So it's fine. So that's an upper bound for error. It cannot be smaller than this. K cannot be smaller than this. Anyway, we put it back into our formula. It is going to be k b minus a over 180 delta x to the 4th power. So we know all the numbers now. K e cubed, b 3 A0 divided by 180 multiplied by delta x 0.5 to the fourth power. Alright, so fraction e cubed 3 minus 0, I just put 3 divided by 180 times 0.5 cube to the fourth power, sorry. And we have so this is an upper bound for error, meaning whatever the actual error is, it has to be smaller than this. So number 3, find the absolute error using Simpsons Rule, so ES. So it's easy. We have this one is an approximation. The actual values we can just put in the calculator. So we subtract. So we have absolute error using Simpsons Rule is an approximation and then subtract the actual values. The actual values I'm just going to use the calculator. So do that. I have this integral from 0 to 3 e to the x. Actually, we don't even need e to the x, right? We enter the function already, so we can just say it. I'm going to put y1 in there. That worked out just fine. So I have 19 point that, and we have the approximation using the Simpsons Rule. So we have that number, subtract the exact values. So approximation minus the exact values, we have that. So this 0.06 43. So this is the absolute error, and this is an upper bound for error, and of course all of the actual error have to be less than that. So this is the worst case scenarios. Likely, usually we're not going to get there, but it cannot be more than this. So, and in fact we find the absolute error is less than an upper bound for error. So this is the worst case. This is the actual situation. That's what we have. Right. So with that, I think I cover everything I need to cover. See you in another video in Calculus 2. As always, thank you for watching.